Hello and welcome to part 2 of this tutorial on HRTF processing in Python. If you haven't seen part 1, please go back to that video to learn how to do basic HRTF processing using wave files formatted HRIRs. So in part 1 we've seen how to use HRIRs to spatialize monosources to desired target angles. Now here in part 2, we're going to do something similar, but through SOFA files. SOFA files stand for Spatially Oriented Format for Acoustics, and it's a portable file format that can be read by different applications across different systems. So they're very popular nowadays to store room impulse responses or head-related impulse responses. So what we're going to use for this tutorial are SOFA files containing HRIRs taken from this dataset. So this is the spherical far-field HRIR compilation of the Neumann KU100. So this website, Zenodo, generally is renowned to keep and maintain a lot of datasets. So you can really find a lot of HRIR datasets on Zenodo. And a lot of them are SOFA formatted. Now, I didn't choose this one for a particular reason, but I thought it was probably a good candidate just to test some of the functions and learn how to process them in Python. And if you read the documentation, you see that they provide different versions of the same datasets, but sample at different degrees of resolution. So you have something sampled only on the horizontal plane for a circle of 360 degrees, something sampled at the Lebedev, no idea how to pronounce this, spherical points of different degrees of resolution, and then something, a sphere sample at the Gauss-Legendre functions with 2 degrees of separation. So all of this is contained inside the same dataset. Now, when we look at the files, inside my HRTF sets folder, I have already downloaded the SOFA far field datasets. And if we open this, we see that all we have is 3 SOFA files. So we have full datasets contained within a single file, which is relatively also low dimensions in terms of size. So we see that the biggest one, it's only 19, almost 20 megabytes. So how do we use this in Python? So in part 1, I preloaded my folder inside my path variables, and I created a variable called SOFA where I'm storing my datasets. So by running this is just telling me where my SOFA files are stored in my computer, and I can use this to access each one of them individually. Now, first of all, we can learn what a SOFA set contains by using this method called sofa.database.open, and then the name of the file path leading to the file. So these are the folders, and this part here is the actual file. .metadata.dump. So when I run this, I have all the informations compiled by the author of the dataset in regards to the dataset itself. So here we can see what is a sampling grid, what kind of dummy head has been used, database name, database type, this means finite impulse responses. You have more information like the organization, the origin, some links. All of this is contained into the metadata of the SOFA file. Now, because they all come from the same authors, if I look at the other datasets, they're going to be pretty much similar. What's different here is the sampling grid. across these 3 different SOFA files. So let's stick to the 0 one, which is the full sphere. And here we go. So by the way, this is taking advantage of this library up here, the SOFA library. And if you don't have the SOFA library, you might need to install it using Python SOFA. So pip install Python SOFA on your Anaconda prompt. And if that has been done correctly, you should be able to import SOFA. Okay. So here we are. Now at this point, I have, for convenience, made a function here called find nearest. And what I'm going to use this for is to find the nearest angle within the SOFA dataset to a target angle that I like. So given an array of angle positions, I will use this function to provide a value, my target angles. Let's say that I want something rendered at degree 211. And suppose that this angle, this particular angle, 211 azimuth, is not part of the sampling grid of this dataset. So this function will be able to find the nearest value to 211 that I want. So that is available in the dataset. So this is how this function will be used. Now, to illustrate the use of SOFA files, I just wanted to make a function that's a little more fun than what was done in part 1, which was just a single source rendering. Here, I'm creating a random display. So what this function will do is choose n number of sources from 1 to 18 and use the SOFA files determined by the set index. So 0 will be corresponding to this first data set. So by changing that number, we can choose and select different ones. At a target sample rate with or without repetition. So what does that mean is we have a set of source files, the ambient sounds that we've seen in part 1, and we can draw at random from that set. Now, drawing at random can be with or without repetition, meaning that we can take away the sample that we extracted from the set and perform a new random choice, or we can put it back in or leave the sample within the set so that it can be selected more than one time. So it's just about reusing the same source samples. If you don't remember the source samples, I think I have a list somewhere here. So this is just going back to the part 1 code, but here we go. So these are going to be the source samples that I will draw from at random. So n random sources from this list will be selected and spatialized at n random positions using the angles available in the spherical data of the SOFA file. So here we have a bunch of traffic sounds, a bunch of domestic animals, some alarms, some crowd noises, some construction sounds, some interiors, some babies and children, other cars, other construction, and so on. All right, let's go back to our function. So this function to run will need to open the SOFA set. And you can use the sofa.database.open and point towards the set that you want to open. From that, you can retrieve, you can see this HRTF variable then can be accessed using these methods. and you can get the values, for example, of sample rate. So what sample rate is inherent to this HRTF. Then I want to retrieve the positions. So what are the angles? What is the list of angles that are provided by this SOFA set? And you can determine a system whether if you want to use spherical coordinates, you have to specify this, otherwise you can use Cartesian coordinates or something else. Now, these variable angles, this is just something that I'm user defining. I'm hard coding this as possible choices of angles in the horizontal plane, possible azimuth choices. I'm restricting this simply for illustration purposes. I want to avoid the chance of having, for example, 5 sources all within a degree from one another, because now I want to maximize my spatial spread so that we produce random examples that have a minimum distance between sources, in this case 10. If you want to reduce this, you can put this number down to 1, and in that case every angle in the 360 plane will be a possible candidate. By putting 10 as an interval here, I'm only choosing angles with an interval of 10, so 0, 10, 20, 30, and so on, all the way to 360, which is 0 again. Something similar I'm doing here for elevations. I'm only choosing, in this case, restricting the choice to 3 possible elevations, minus 45 being a lower elevation, 0, and 45 being an upper elevation. Keep in mind that you need to know a little bit about the data set, first of all. So I know that this data set uses negative numbers for lower elevations, so I can put a minus here. Some other data sets, they have a 360 elevation convention, so you will see lower elevations with a very high number like 330. And 330 might stand for minus 30, but it depends on what kind of values are stored in the SOFA file. So you might want to go into the documentation and make sure what possible values, what is the convention of values that is used to represent each source position. Now, the next thing here is to create a list of my sources so that I keep track of how many sources I'm spatializing. And finally, I am creating placeholders. So empty arrays made of zeros that I will use to progressively fill my 3D binaural mix, my stereo mix, with spatialized sources. So each time I will recursively, or better, iteratively spatialize a source, I will put it in these placeholder arrays, which will build over time according to how many sources I'm going to put inside and how long these sources are over time. So you got to start with something in order to make this progressive filling and progressive build-up of the final mix as you go along. You don't have to do it this way, but this is something I find convenient. So here we are at the main loop. So what happens here is that we're going to iterate n times, with n being the total number of sources that we want to spatialize at random angles. And each iteration of the loop will correspond to a spatialization of one source. Now, the first thing that we do here is to select a random angle out of the possible set of angles that we defined here. So something between 0 to 360 at 10 degrees interval. So we retrieve that angle, and then what we do next is remove that angle from the set of possible angles that we can choose at the next iteration. So I want to avoid having two sources being spatialized at the same azimuth. So to avoid that, I will remove the angle I've chosen now from the set so that I don't choose it again. And not only that, I will also remove the front-back complementary angle. Now, because we experience front-back confusion when we listen to static 3D audio, I don't want sources to be presented both at the front and the back complementary position. So if I have a source, say 20 degrees on the right, I also do not want to have a source 160 degrees on the right, because those angles are complementary across the front-back plane. And since I want to avoid confusions, I want to avoid having that sort of perceptual possible confusion with sources possibly being perceived as coming from the same angle, I will also remove that complementary angle from the list. So two angles are removed at every choice. So when you do that, I'm first checking where my random angle has been chosen, if it's before the 180 crossing point or after. And if so, I'm finding the distance from the plane at the frontal plane, which crosses 90 and 270, and find the complementary position of this angle. So the distance from 90 towards my angle of choice, reflected and mirrored on the other side of 90 degrees, is where the complementary angle will be. If the angle we chose initially is beyond 180 degrees, then instead of 90 as a reference point, we use 270. And we also find the arc and the complementary angle using the arc. Now there's a special case that we choose exactly 90 or exactly 270, and in that case, no complementary angle exists. So unless we are covering that special case, we're also going to delete the complementary angle whenever it exists. So now that we have removed the angles, we can be sure that at the next iteration, we're not going to choose the same angle again or the complementary angle for the next source. The next thing I'm doing here is just some database specific format adjustment. This is very specific to this dataset. The azimuth convention is anti-clockwise instead of clockwise. So again, this is something that needs to be checked in the documentation of the HRIR dataset. And in this case, a simple fix is just to subtract my chosen angle to 360 to obtain a new angle, which is in the anti-clockwise convention instead of the clockwise convention. If I am exactly landing on 360, I set that as 0 so that everything is within the expected formatting of this database. So now that we have chosen our azimuth angle, we can choose our elevation angle at random inside the set of elevation angles that we defined earlier. So it will choose one of these three numbers at random, -45, 0, or +45, bottom, mid, or higher plane. Now in this case, I'm not removing any angle because it's just three possible heights, and it's okay if they repeat because the azimuths are going to be different anyway. So there's enough of discrimination level even though we have sources at similar heights next to each other. So now that I have my randomized angle, my randomized azimuth choice and my random elevation choice, I need to find the HRTF available position that's the closest to that angle. So my exact choice, my exact random choice in this case might not be present in this data set. So we can use my find nearest function defined earlier to find that nearest angle that exists within the set. So recall that I defined a variable called positions, which is this ones, which retrieves all the source positions available in the SOFA dataset. Now here, I am calling that function on those positions, reading just, for now, the azimuth. All the azimuths in that data structures will be stored in the first columns. And to verify this, you can simply create another cell where you extract these positions and you print them. And you will see that all the rows of the first column correspond to the azimuth angles of the HRIRs available in this dataset. So here I'm retrieving the angle and its index inside this array. That is the closest to the angle that I randomly chose earlier. Now, what we need to keep in mind is that there will be more than one single position equally distant to my azimuth. So my SOFA dataset will contain many angles at the same azimuth, but all at different elevations. Now this function is only going to give me the first index of the closest azimuth, but that is not necessarily the one at the correct elevation. So what I'm going to do is create a subset of positions containing all the positions at the azimuth level that I found to be the nearest earlier on. Right? So first we use find the nearest on the azimuth. We'll retrieve the actual angle that we can use. Now we create a subset of all the available angles in the SOFA set which do possess that azimuth that we found. Now within that subset, we can find the one, the HRIR at the right elevation. And we get a subset index, which will be added to the first index for retrieving our final HRIR that corresponds to the azimuth and elevation that we look for. And again, we use the find the nearest position, the find nearest function, but this time we apply it to the subset. And of the subset, we apply it to the second row. Second row will have to do with elevation. And my target elevation is what has been chosen here at random from the 3 possible choices that we had. All right, so after these 3 lines of code, I found the indexes that will point me to the HRIR closest to my target values. And here I retrieve the data. So H0, meaning the left channel for the left ear of the HRTF, is retrieved like this. I define the indexes of what I'm looking for using the method data.ir.getValues. You have to use this format, and here is the index of the measurements that we want. Azimuth index, which points to the first angle with the right azimuth, plus the subset index, which when you add it to the azimuth index points to the one with the right elevation too. Now I can do this here because I know how this dataset is structured. Some datasets might be structured a little differently, but I know that at least these three that I have loaded here, they are all organized in this way. So this algorithm will work. I do not guarantee that it will work on different SOFA files. You might have to understand what is the order of the positions, how are they structured, what is the definition of these measurement indexes in itself. But we can assume most of the time it will be something similar to what we have here, and it allows us to do it in this way. Now the second number here is the receiver, being 0 because is the first channel, the left here, and the emitter 0. In most cases, the emitter will always be 0. It depends if they're using different speakers for their measurements. Again, it has to do with the specification of the HRTF dataset itself. So do read the documentation to know exactly what they're doing. In this case, I know they use a single speaker, so emitter will always be 0. Finally, do the same thing for the other channel. Now, this one here symbolizes the right channel, the right here of the dummy head. And we retrieve the data using the same function. Finally, I resample to my target sample rate if necessary. And as we did in part 1, we use librosa.cord or resample, yada, 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 what you need to do to get this H variable, this HRTF data sample at the correct sample rate that you need. Finally, we pick the sources. Now, out of the list of sources that I had earlier, I'm going to pick a random source out of the list, and I'm going to read it using sf.read. This is my global variable that contains all the list of sources, ambient sound sources that I showed earlier. So now what I'm going to do is, first of all, collapse my source to mono in case it's not a mono file, because I want to spatialize this as an object. So I take the mean of the channels. And then I check this repetition variable that I had at the beginning to see whether I want to delete this source out of the possible set of choices for the next iteration of the function. So if I do not want the repetition, I take it out from the set. Okay, then finally, I have here sample rate check, just the same as for the impulse response. We are doing the same here for the source. If it's not my target sample rate, resample to the sample rate that I want and save inside the same structure. So at this point, we have our source file in variable X and our HRAR in variable H. All right, now we're ready to perform the actual convolution step. So I'm creating two variables which contain the rendered version of the convolution between my source signal X and each channel of the HRAR. So in this first line, I'm retrieving the left channel, which is the first column at index 0. And in the second line, I'm using the right channel, which is the second column at index 1, to create my left and right spatialized version of my source. Now here, after I do this step, I'm retrieving the maximum point out of these two channels. The reason I'm doing this is because later I will use this maximum point to normalize and scale the amplitude of the rendering to peak at 1. And this serves two purposes. First purpose is to avoid clipping by not having the signal go beyond the values of +1 and -1. And the second purpose is to try to scale the amplitude of each source to have almost equal loudness among sources in my sound field, and avoid having sources that are much louder or much quieter, and try to give some sort of normalized scale to everything. Now, this is definitely not the smartest way to do it, because you might have transients that are very loud compared to the rest, and those would skew the normalization that I'm doing here. But in this case, I do not care that much to do it correctly. So just to do it a little bit more cheaply on the fly, I'm going to normalize using this. So the next step is simply about putting these rendered versions inside my placeholder array that I created earlier. So this array at the first iteration is just full of zeros. And first of all, I check if I have to pad this array with more zeros by checking how long my rendered versions of the source are. If they're longer than my zero padded array, I'm going to zero pad more, so that my placeholder array becomes longer in response to the length of the audio file that I just convolved. Now that I adjusted the length, I can insert the rendered files, the rendered left and rendered right channels inside my placeholder array. So I simply indicated the indexes of insertion, so from 0 to the length of the render at channel 1, at the left channel, and at the right channel. And you can use this plus equal to add in this slice of the array this new audio that we created, scaled by m, which is our normalization factor, and add it to whatever is pre-existing in that placeholder array at that same point. So of course, the first time we run this, those array numbers are going to be zeros, because we filled this with zeros. So we are adding a new spatialized sound to a bunch of zeros, and this is going to be equal just to that first sound that we create. Now at the next iteration, when we spatialize the second source, that second source will add and mix to whatever was pre-existing within that level in the first place. And finally, we have just a print operation here just to keep track of what's going on. It's going to tell me, at every iteration, it's going to tell me which source is being spatialized and which angles have been chosen for the spatialization, so that when we listen, we know if things match the expectation, and we know that everything is correct. All right, so let's run this. And function looks okay. And now we can call the function. So here's the example. Now remember to wear headphones, otherwise you cannot appreciate the spatial character of the sound. Sample rate is defined at 48K. And here is my usage of the function that I just coded earlier. So I'm creating a variable called binaural, using my function random display, choosing the number of sources, in this case 3, choosing a SOFA set, 0, 1, or 2. I'm just choosing 2 just for fun. There's no particular reason. My target sample rate is going to be this one, 48K. And I think there was another argument here, repetition equal false. I'm gonna keep it as it is. I don't need to define it necessarily if I want to keep the default value, which is false. So I'm gonna keep it as false so we don't have repetition of the same sources. Well, we don't have the possibility of repetition of the same original sources. So finally, we use the audio function to listen within the notebook what we have created. So let's compile this. Okay, so we have three sources here. First one is a car render at azimuth 260 and elevation 0. I already prefixed these labels to be in the clockwise direction. So this 260 will be the rear left, pretty much close to full left, and elevation 0. Then we have a bus at azimuth 120, so the rear right at elevation 0, and another car at azimuth 340, so the front left, elevation minus 45, so at the bottom. So just by chance, we picked three cars, three vehicles in this sound field. Now let's listen. And of course, some of my original samples, some are longer than others. So you hear one ending earlier than the other ones do. It's just a matter of matching those lengths to avoid that effect. But you heard for the first at least 10 seconds at the beginning, they were all three sources were active. Just for the sake of seeing what else we get, let's run this again. So we have a bus, we have a car, we have a dog barking, and we have everything in the upper elevation, 210. That's the rear left, front right, maybe full right, and rear right. Okay, that was definitely easier to detect all the three sources. And this is because the sources being enough different with each other, there's less of a risk of frequency masking that may happen when sounds overlapping frequencies too much. We can increase the number of sources just to play around with it. So I'm gonna go up to 7. And here we have interior crowds at azimuth 30, front right, street crowds on the rear right, a bus in the front right, a car in the front left, babies and children in the back right-ish, nail being hammered on the rear left, and a dog barking in the front left, maybe full left. So let's see what we get. Alright, definitely a very complex sound field with a lot of sources. It's hard to detect each source individually because of the busyness of this sound field that we created here. But you could clearly tell kind of the energy directions of each source or class source sources. So there was a little more energy on the right than the left, And then you could tell that when some sounds die, then you suddenly notice a sound that was hidden by another sound. Um, Hopefully, spatialization can help with the discrimination of those sounds. So there's something called spatial release from masking. That means when the sounds are enough distance in space, then frequency masking is less effective, and you suddenly can discriminate sources better. But it's hard to tell here what exactly is needed as a spatial separation to create that discrimination that we seek. Let's just go up in sources just for the sake of the exercise. I'm going up to the maximum 18 sources. So there would be basically a source every 10 or 20 angles using this function. And I challenge you to detect all 18 sources, because that's going to be very unlikely. Human perception can cap at a certain number of sources, and these sources being sometimes similar to each other, it's really hard you find somebody able to detect all 18 of them. But let's give it a shot. Let's see how it sounds like. Okay, that was definitely very busy as a sound field. Let's run a different one just for fun. So those are all different sound sources. Remember, I don't have repetition. And we have a little bit of everything here: construction sounds, cars, crowd sounds, dogs barkings. All right, that's quite a busy sound field too. All right, so the next thing that I'm going to show is how to do the same thing but manually. Let's say you want to choose exact angle positions, exact elevation position, and exact source IDs. Like, I want these footsteps to be here, I want the car to be on this left rear side, something on the front. Here's a function that allows you to do this manually, which running kind of similar to before. So I'm not going to go over everything that is the same as the other function, but what changes is that you need to define arrays as your inputs. So an array of azimuths, an array of elevations, and an array of source IDs using the list that I had earlier. And those arrays feed directly into the choice of the angles. So there's no random selection, there's no random set. We don't need to delete angles from the set. It just iterates one by one through all the information that we feed to the functions. The source is not random. I left this word here. The source is taken from the source IDs that are given as an argument here. Everything is pretty much the same besides that. So let's see how to make use of this function. Let me compile the function, and before we do that, as a reminder for myself, I just want to print all the sources that I have so I can choose the IDs of the sources as I want them. And here they are. So let's make an example manually. Let's say I want 3 sounds and 90 degrees of separation from each other. I I choose my variable, I create a new variable, and this other variable, the other thing I'm returning is the positions, right? So I'm also retrieving those positions in case I want to use them for something later. I'm not really using them here, but it's just an extra return of the function. Then I call manual display, which is the name of the function, and I have my azimuth degrees, 90, 180, and 270. My elevation numbers, just arbitrary, 0, 20, minus 60, and the source IDs, so 8, 33, and 14. Those stand for collie dog barking. 33 is an electric drill. 14 is hammered nails. And keep in mind that there is a position match for each ID to their angle. So the dog, which is ID number 8, will be spatialized at 90 at elevation 0. And the hammer nails, which is ID number 14, will be spatialized as 270 at elevation minus 60. And here, this little one is just the SOFA file that we're going to use out of those three. I can put these 0, 1, 2, they all should work. So let's listen to the example now. I created a sound field where I have full control of my angles and full control of my sources. All right, so you could hear a dog barking on the right, nails being hammered on the left, and a drill pretty much in the center, which is a 180 full back. So that's what we wanted. Adding another source is pretty easy. Say you want to add, let's see what we have. I think there were footsteps somewhere around here. Let's see if I can find them. There we go. So number 31. Just add source ID 31, and let's make them coming from the front right. So 35 degrees. Oops, make a comma here. And I want them at, let's say 40 degrees elevation, just for fun. Now we're going to have an extra source in our mix. 1, 2, 3, 4. Let's see. All right, so this is it for part 2. I hope this was useful and educational. Mostly the main point I wanted to make is how to handle SOFA files and how to make use of them. And this whole random binaural display is just a fun application that we can use HRIR for to create these sort of artificial sound fields starting from mono sources. All right, so this is it, and I'll see you in the next video.